Perhaps the most important use of mass to mole conversions is in the area of what we call stoichiometry. Stoichiometry is the measure or study of the relative amounts of materials involved in balanced chemical equations. We're going to talk about stoichiometry and the related idea of limiting reagents, and you can read about this in sections 6 and 7 in chapter 3. So let's start by reviewing the meaning of a balanced chemical equation. Chemical equation is shown here, the stoichiometric coefficients. What those mean are that one molecule of methane reacts with two molecules of oxygen to produce one molecule of CO2 and two molecules of water. But that's not a unique way of balancing the equation. I could multiply the entire equation by 2, multiply all of the stoichiometric coefficients by 2, and it would still be balanced. Or if I like, I can multiply by 12, so that I have 12 molecules of methane reacting with 24 molecules of oxygen to produce 12 molecules of carbon dioxide and 24 molecules of water. And if I'm going to use 12, I might as well refer to this as a dozen molecules. So this is the same thing as saying 1 dozen CH4 molecules react with 2 dozen molecules of oxygen, etc. And once I get that word dozen in there, it makes just as much sense to use the word mole. So if I multiply the entire equation through by Avogadro's number, then I have Avogadro's number of CH4 molecules. That's 1 mole of CH4 has to react with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. So here's the key concept. Balanced chemical equations indicate the mole ratios of the chemicals involved. So if we want to relate the amounts of substances in equations, we have to use it in terms of moles because it's really about counting molecules. And in order to avoid counting really small things, we just use moles. So why would we care about the amount of substance in an equation? Well, perhaps you need 10 grams of a certain product. How much reactants do you have to get in order to produce that? Or maybe you mix two chemicals and you want to tell how much product gets formed. That's the sort of idea behind this. That's what we want to be able to do by using balanced chemical equations. So stoichiometry is the use of balanced chemical equations to relate amounts of chemicals involved in a given chemical reaction. So using our combustion reaction of methane, remember combustion is just the reaction with oxygen to produce carbon dioxide and water. And here I'm showing you the balanced version. We balance it again to keep the same number of carbon atoms on each side, same number of oxygen atoms. What if we wanted to know how much water is produced by the complete combustion of 1 gram of methane? Our outline of attack is going to be, we start with the mass of methane because that's what's given in the problem. But we have to convert a mass into moles. We have to do that because the balanced chemical equation only tells us something about the ratio of moles. So we first have to convert to moles of methane. We're going to use our balanced chemical equation to convert that into the equivalent number of moles of water. Once we know the moles of water, we can use the molar mass of water to convert that moles of water into the equivalent mass of water, and that allows us to complete the problem. So let's see. So if we do this, we start with our 1 gram of methane and multiply it or divide it by the formula weight. We'll cancel out the grams of methane with grams of methane. That will give us moles of methane. We then use the stoichiometric ratio. This factor here is called the stoichiometric ratio. And we get the numbers here literally from our balanced chemical equation. There's 2 waters. That's where the 2 comes from. There's an implied 1 methane. That's where the 1 comes from. We literally just read those numbers off our balanced chemical equation. That cancels out the moles of methane and leaves us with moles of water, which we can then convert using our molar mass of water to cancel out moles of water and leave us with the units that we want, grams of water, And when we round to the 3 significant figures that we need, our answer is 2.25 grams of water. Let's see one more example of doing this. What if we want to figure out what mass of oxygen is consumed by the complete combustion of 1.00 grams of propane? Now, stoichiometry relates any substance in a balanced equation to any other substance. It doesn't have to be reactant to product. It could be reactant to reactant, product to product, reactant to product, product to reactant. Anything can be related by a balanced chemical equation, but we do always need a balanced chemical equation. So our first plan of attack is to write the chemical equation. To do that, in this case, you have to remember the formula for propane. Okay. Once we have written the balanced chemical equation, we balance the equation because it has to be balanced. Once it's balanced, we can use the stoichiometric ratio from a balanced chemical equation to complete the problem. So let's see how we would do this. Let's see. Here is a generic combustion with reaction with oxygen, carbon dioxide, to produce carbon dioxide and water. We first have to balance this. So 3 carbons on the left, that means we need 3 carbons on the right. And then we've got 8 hydrogens on the left, we need 8 on the right, so we multiply the water by 4. Count up the oxygens on the right, 3 times 2 is 6, plus 4 is 10. We need 10 oxygens on the left, and we would get that if we multiply the oxygens by 5. Once we have a balanced chemical equation, we can then set up our problem. So we take the grams of methane, divide that by the formula weight of methane. Again, the grams of, sorry, I said methane, I meant propane. Calculate the, cancel the unit of grams of propane, that converts to moles of propane. Then we set up our stoichiometric ratio using the balanced numbers here. The 5 goes with oxygen, the 1 goes with the propane. That cancels out moles of propane and converts it into moles of oxygen. Once we have moles of oxygen, we can use the formula weight of oxygen to convert it into the mass of oxygen, rounding to 3 significant figures because that's what we have in the problem, and that's how we set up our problem. Now, a complication in these sorts of calculations comes when we are given the amount of both reactants in such a problem, and that leads to the idea of limiting reagents, which we will see on the next slide. If a problem gives us the amount of both reactants, then we have to figure out which one runs out first. Whichever reactant runs out first is referred to as the limiting reagent. So to start with, as just an analogy, again, if we had 3 slices of ham and 9 slices of bread, how many ham sandwiches could you make? Well, assuming 1 slice of ham per sandwich, I'm sorry, I like more than that, but let's just go with that. If you had 1 slice of ham per ham sandwich and you had 3 slices, you could make 3 sandwiches. If you have 9 slices of bread and you assume 2 slices per sandwich, you could make 4 sandwiches. The ham is what limits the number of sandwiches that you could make. So we refer to the ham in this situation as the limiting reagent. It determines how many sandwiches can be made. We have similar situations in chemistry, of course. Again, if a problem specifies both amounts of substances, 2 grams of zinc is dropped into a solution containing 5.98 grams of silver nitrate. I've told you the amount of both reactants in a balanced chemical equation. One of those is going to run out first. Which one is it? The question is, how many grams of silver will form? Silver is this product. Don't just think of silver as anything containing silver. Silver is this. How many grams will form? Well, it's going to be limited by whichever reactant runs out first, and we have to figure that out as we go. So the way we do that, we're going to calculate an actual ratio of moles of silver nitrate to zinc and compare it to the ratio of silver nitrate to zinc that we actually need in the problem. Now, the order of the ratio that you calculate is not particularly important as long as you calculate the same ratio both that you need and that you actually have. So the first step here is to calculate the number of moles of zinc, which I've done here, and calculate the number of moles of silver nitrate using the formula weight of silver nitrate. The second step is to calculate how much zinc to silver do I actually need. Silver nitrate. Well, let's see, let's calculate this. Let's do, I need, let's see, what order do I want? I'm going to calculate 2 moles of silver nitrate. I need twice as many moles of silver nitrate, that's supposed to be a 3, for every 1 mole of zinc. These numbers are coming from the balanced chemical equation. This is the stoichiometric ratio. That's how much I need to exactly react. Now, how many moles do I actually have? What I actually have, keeping it in the same order that I just calculated, I take the number of moles of silver nitrate, calculated from the amounts in the problem. So silver nitrate, and I divide that by the actual number of moles of zinc in the problem. So this is coming from those numbers. Plug that into my calculator and I get 1.15. What does this tell us? Up here, I need twice as many moles of twice as many moles of silver nitrate as zinc. That's what this ratio tells me. But I only have 1.15 times as much silver nitrate as zinc. I don't have enough silver nitrate. And that's why silver nitrate is the limiting reactant. So there's not enough silver nitrate to react with all of the zinc. That's what we mean by a limiting reactant. Now let's complete the problem as requested in the previous slides. The question is how much silver gets produced. So now that we know what our limiting reagent is, we can use the limiting reagent, and you have to use the moles of limiting reagent, not the moles of anything else, to set up our problem. So we take our number of moles, 0.0352 moles of silver nitrate. We convert that into the equivalent number of moles of our target substance, in this case silver itself. And yeah, 2 divided by 2 is obviously 1. I'm not entering that into my calculator, but just for formality, we show that we cancel out the moles of silver nitrate, replace it with moles of silver. Then we use the formula weight of silver to replace the moles of silver with grams of silver. We round our number to 3 significant figures, so that last 0 is important for significant figures because we started with 3 significant figures in the problem, and that's how we complete the problem. And this is, we have to use the limiting reagent again because that's the whole definition of limiting reagent. It limits how much product gets formed. Now just a few more terms that are important in this section. By theoretical yield, what we mean is the amount of product formed from the limiting reagent as predicted by stoichiometric calculation. That's what we've got here. 3.80 grams silver in this case is the theoretical yield. But sometimes when you do an experiment, you don't actually get what you're expecting to get. What you measure as a result of an experiment is the actual yield. Maybe you only get 3.7 grams of silver. Maybe you missed some of the silver when you measured. Who knows? But it's typically different than the theoretical yield. So that we say that the percent yield in a reaction is just the actual yield, the amount you measured as a result of an experiment, divided by the theoretical yield, the amount that you would have expected from stoichiometry, and converted into a percentage.